that an experiment that has only two types of outcomes. It's either a success or failure. There is no other option to have it. And it's really easy to calculate the expectation and the variance because we are always interested only in the successes. So if we know that the success is P, the expectation should be the same, just P. The variance, we're gonna calculate it like multiplying the probabilities of success times the probability of failure, which is if the success is P and the whole sample is just 1, then the probability of failure would be 1 minus P. So one tiny exercise using those formulas above, if we have if we have an experiment and we know that 55% of our populations is just male, and male we're gonna denote it by just M, capital M. Then we're given that 78.2% of females in our populations in the labor force do paid work. Then we know the percentage of females that do the same paid work. And we have to calculate the probability of having X being equal to 1 when we know that 1 means that that person is taking part in is doing paid work. And X equal to 0, it means that it doesn't. What would be your suggestion if X being equal to 1 is the probability of success in our case here? What is P and what is the probability of having X equal to 1? We're given male and female are separately taking part in the force, in the labor force, but we have to calculate in some together what is the probability of having male and female doing paid work. Do you want me to start explaining or just try it yourself?
If you can explain it.
Yes, sure. The important part is to understand that X1 is our probability of success. Success means having people that do paid work. But in our case, people, we don't have just people. We have male and female that are all people. So we need to compute the sum of all men and women doing paid work. And we are given already some percentages, so we just have to use them to calculate it. The first part is having only males doing paid work. So that is X1 intersection with men, which means that this thing is already given here. The men that do paid work, but we have to find, and the women that do paid work. But here we have to find M complement because if it's not men, it's a woman. It's not, there is no third choice for that. Then here we would have the probability of having X1. We already told that is the success given men. So which means that percentage is 78.2% times the probability of men, because that's how the intersection is being calculated from the formulas before that we know. This thing here equals to this part. And it's pretty much the same with the females, which are men complement. This part equals this one here. And this, it's a mistake. That's not should be there. It's just once. And then we have all the numbers. We just have to compute them and be careful because here for the M complement, we have to calculate the number of female because we're given only the male. if the male is 0.55, it means that the female should be 0.45. It's just 1 minus the male. And we just take the males doing paid work, which is here, times the probability of having the man, which is 0.55, which is here. Then we have to compute for the women. We are given that the women doing paid work are 58.7%, which is here, times having all women. And all women are 1 minus the male, which is 0.45. And if we calculate it correctly, we have to take the end result as 0.69. And now comes the easiest part. We have to determine the expectation, the point B, the expectation of X. But we already know from the formula that the expectation is just the probability of success. And in our case, the probability of success is having paid work. It means if someone do paid work, it's success. If it doesn't, it means it's a failure. So we just have to equal it to P. And in our case, we already found P, which is 0.69. So we just copy and paste the same number as in A. Those two numbers are the same. What we should do to find the standard deviation here? We just have to compute the variance, because the standard deviation is always like a subcalculation from the variance. It always follows from the variance. You cannot find it otherwise. To calculate the variance, we just need, again, only P. And P in our case is 0.69. And we just take 0.69 times 1 minus 0.69. That will be the variance. And the standard deviation is the square root of the variance, which is that number here. How did you find this exercise? I'll wait for a second to take notes, and then we're going to continue to the second distribution, type of distribution. So here we can imagine the same scenario. Forget about all definitions, just want to remember what it looks like to have such a distribution, not just the definition. For example, you're going to Albert Heijn, and you're set that the probability of having a beer there, of buying a beer, is 0.6. But if we imagine a whole experiment, many people go to that supermarket. And let's imagine that the total number of students going to the same supermarket is 100. And our event Y is the number of students buying a beer. If we know that the total number of students is 100, and the probability of having our event, which is Y here, is 0.6, what would be the probability of having 70 such students going to the supermarket and having a beer? Maybe I should start. The first slides, we're going again back to the first slides, to the orderings. We have to take 70 students having a beer from all of those which are 100. So it means that the probability of having exactly 70 students having a beer is equal. What do we know? We have to take from all of those 100, only 70 that buys a beer. What we should do next, we have to multiply by the probability of buying beer, which is 0.6. But here we have to be careful because here we have 70 students buying a beer. So it means that here 1.6 won't be to the power of 1, but it should be to the power of 17, because that probability goes for those 70 students that buy a beer. We have to multiply again by the probability of not buying a beer. What would be that probability if we know this one is 0.6?
0.4.
Exactly. 1 minus 0.6, which is 0.4. And we have to take it to the power of which number?
30?
Yes, because if we know that 70 are buying a beer, it means that 30 of them are not buying. And we just have to calculate this number. That is the whole formula to calculate. But I think just to get the meaning behind it, it would be easier to copy and paste in the next exercises if you have them. Do you want me to explain one more time or it's fine? I don't see anything in the chat, so I will continue. Next part, it asks us for the expectation of y. The expectation of y, the formula is here, is n times p. And now we have to see what n means and what is p. When we have such a distribution, it's denoted by binomial distribution, and in brackets, n, which is the number of participants, the number of students going to the supermarket, which is 100, comma, the probability of having a success. And a success in our case is buying a beer, which is 0.6. That is our distribution function, how it is denoted. We know n and we know p, so we can easily calculate the expectation of y, which is just n times p, which would be 100 times 0.6, which would be equal to 60. That's just the expectation of having success. We just multiply this number by this number. Then, if we have to calculate the variance of y, I'm sorry, that's y, not x. We have to use, again, only n and p, but this time, the variance, we have to take into consideration the probability of having a failure, which is minus p here. We have n, which is 100, times the probability of having a success, which is 0.6, times the probability of having a failure not buying a beer, which is 1.4. And in that case, if I'm not wrong, that should be equal to 21. Yes, sorry. 6 times 4, it's second grade. And that is all in case we have 60 students buying a beer. What would be the answer if we know that 70 students, we know to find the expectation of y being equal to 17? What would be the expectation? And then the variance. If we have 70 students buying a beer from 100, it means that the probability of buying a beer, it becomes 0.7. So that's a different option of the exercise. And when we know that the probability becomes 0.7 and the number of participants, which is 100, doesn't change, it will become just 17. But that's in case we have 70 students buying a beer out of 100 again. And here I had a few formulas written down for proportion of successes, which I'm not sure if you had before exercise with it, but I was looking and I couldn't find an exercise about those, but I thought it's going to be useful just to have the formulas here around. Maybe I can explain with a few sentences without an exercise. If we have the proportion of successes, we have Y as the event that we are interested in, and N being the total number of events that could be resulted in our experiment. So the proportion of success is having our event over the total number of events, yes. The expectation is again P as the normal distribution, the previous slide. But here, the variance is P times 1 minus P, but this time over N, because we are looking for proportion. We have to take in mind that this is part of the whole set of probabilities and whole set of outcomes. And when we're looking for proportion, we have to divide by the total number, which is N in that case. And now we are going to another type of distribution, that's the exercise. Okay, which is uniform. And that's maybe the easiest part because everything can be shown in the graph and just it's rectangles. They're not weird forms, weird formulas, and anything. Those are the formulas, but if you look at the graph, you can come up with them on your own. It's not necessary to remember them. So in our case, we have f of y, and we have that our function has this result in case it's between a and b and beta, that it's constant here. And 0 for any other number that is outside of those intervals. So we have constant line here, and everything else is just 0. We have to calculate again the mean and the standard deviation. If we know that those numbers here, that's 100 and that's 500. What does that mean? We have the interval, and we have to calculate the mean, the number that is in the middle of our interval. That's just the average, the middle point. What would be that number if we know that A is 100 and B is 500?
300? Or no?
300?
Yeah.
Yes. Okay, we get the mean. Now we have to find the standard deviation. But if we have to find the standard deviation, we have to find the variance. So it's basically, we have to find everything. In that case, the variance, we can calculate it, but having the maximum point, which is 500, minus the minimum point, that is 100, the whole bracket to the power of 2 divided by 12. If you ask me why it is 12, I'm not sure I can give you a straight explanation. It's just better to remember that this whole part is to the power of 2, and then we have divided by 12. We again use only those numbers because we have to calculate the variance. And from here, it becomes 400 to the power of 2 divided by 12, which would be around 1333, 333.33. And now the standard deviation is just the square root of this number. If we imagine that here that graph represents the profit of a shop, and the accountant of that shop says that 50%, so half of the days, they have profit below 300, which is our mean, our average. Here is 300. They say that that part is 50% of the whole area. Is that person right or wrong?
That is right.
Just yes or no. I won't require any explanation or something. Just yes or no, just a random answer.
Yes, yes.
Okay, he's right. And why? Because it says that half, exactly half, but we know that the mean is the middle point of our interval. So we have 50% here on the right, on the left, and then 50% on the right. So he is right. If we have our profit below 300, it's exactly the half of our interval. And if it says that 50% of the days are above the mean of 300, it would be the same. He's right, because that's exactly the middle point. That's one half of the whole thing, and that's one half of the whole thing. Now we're gonna continue with an exercise again. And I want to give you 5 minutes maybe, or even maybe 7 to read the question and try it on your own. start by drawing just the graph. Did someone get the variance and some number? Yes, exactly. 8.333 at the end. Yeah. So we just when you see an exercise with an interval, just write the graph, and from now on you will be fine. First, we have that data constant between 4 and 14, and it means that we have a rectangle, but we don't have that number here. But we can easily calculate it because this part here is just 10. And 10 times that number here should be equal to 1. So this number here should be 1 over 10. Then the formula for the variance, if you remember from the previous slide, is just having the maximum point, which is 14, minus the minimum point, which is 10, to the power of 2, divided by 12, which is just, here it should be 4 instead of 10. It should be 100 divided by 12, which is just 8.33. We have to continue to b. Now we have to find the probability of having x between two certain numbers. That's also easy because we can just type in those numbers in the graph and see how the graph goes. The first number is 8.7, which is somewhere here, for example. The next number we see is 15. But if you remember, if we have something outside the interval, it's just 0. So 15 is somewhere here. But if you have 15, the result will be just 0. So we have the last, we have to take the last available point that we have, which is just 14. And our interval becomes this one. It says between 8.7 and 15, but here we don't have that. That's 0. So we can easily calculate it. And why? Because we have that part. It's just 14 minus 8.7. Then we have to multiply it by the height, which is 1 over 10. And that's it. We don't have triangles, that's just rectangle. And if I'm not wrong, that should be 0.53. Did you get that number? Great. Awesome. So now we have the area, but we don't have the number inside the brackets. What can we do? Do you have an idea? We're given that just the area is 0.15. And we have to find on which number above the area is that is 0.15. If we know, for example, let's put here B. The area above B would be the whole part here. And we see that's the majority of our area. So it should be more than 0.15. So B is not here. B is more towards the right hand side. let's imagine it's somewhere here. So that area, now it's possible to be 0.15. And what can we do? We just substitute and take the formula for a simple rectangle. The first side is 14 minus b times the height, which is always 1 over 10. And we know that that area equals the number that is given, 0.15. We have one variable, we can easily calculate for b. And if it's calculated correctly, the end answer should be 12.5. Okay, so now we're going to continue to another exam exercise, which is again the same type of graph, but with different numbers and maybe a bit more difficult because we have big numbers, not just 4 and 10. I'll give you 5 minutes to read it and see how it goes. Did you get to point B or C?
I have made A and B. So.
I made A, B, and C now.
Do you want to start with A? I will start, okay. So we have to find the basic, the expectation and the variance. The expectation, we know it, that it's the minimum point plus the maximum over 2, because that's the mean. And that's just 20. If we have to find the variance, we just also need the maximum point, which is 22, minus 18 to the power of 2 over 12. That's just the formula. Having the maximum point minus the minimum to the power of 2 and then divided by 12. And the number should be equal to 4 over 3. If we have to continue to determine the function of 17, what we know? We know that from 18 to 22, there is a constant line going. But other than that, we have just zeros here and zeros here. So it asks us for 17. 17 is somewhere here. So it's just 0. It's outside our straight line. So this here is just 0. F of 18.5. That's something different. We have 18.5 somewhere slightly after 18. We just take the line here and we have to find that area that is here. That's really simple, having just 0.5, because that's that side, times the side that is here. But do we know it? We don't know it, but we can find it. And how? Because we know that the whole thing here is just 1. That side is 4, so that should be 1 over 4. That big side here. So it becomes 0.5 times 1/4, which is basically 0.125. Then we have to find a conditional probabilities. That's using the formulas that we had in the first slides, but we're gonna adapt them to our graph. Firstly, I'll erase this part here, not to get it confused. So, if we're having the conditional probabilities, what do we have? Firstly, we have to have the intersection above between those two probabilities, which is x being less than 19.3 and x being more than 19. What does it mean? It means that we should have the probability of having x between 19 and 19.3. That's the intersection between those two events. And in below, we will have the probability of having x bigger than 19. And why? Because that's the second event here, x being more than 19. How to calculate the x being between 19 and 19.3? Just plug in the numbers in the graph. Here that would be 0.3 times the height, which we already found, which is 1 over 4. Then we would have below the probability of having more than 19, which is everything that is here. And that is that side, which is just 3 times 1/4. And we can just queue those two because they're the same numbers, and we would have 0.1, 1.3 divided by 3.
Why do you?
Do you want me to repeat anything?
I have a question.
I'm not sure if drawing with my pen on the presentation is clear enough and understandable. So let me know if something is pretty badly written. Now we're going to continue to part D. We're given that we have to select randomly 40 balls that are produced by the machine, and the number that we're interested in having diameter larger than 21.2. So it means our number is somewhere here, 21.2. So what kind of distribution does Y have? We randomly select them here. If we think about, we had before the probabilities of having a success and then a failure. And if having a success means having a ball with diameter more than 21.2, that would be just having a binomial distribution. And how is the binomial distribution denoted? We just have to take the number of all participants in our experiment, which is 40 balls, and then the probability of success. But we're not given the probability of success, so we can calculate it. We just have to find here. That area is just that side, which is 0.8 times the height, which is 1/4. So 8.8 times 1/4 should be equal to 0.2. And that is our chance of having a ball with diameter larger than 21.2. So in the end, the parameters of our binomial distribution is Y, the binomial distribution of 40, which is the total number of balls that we're having in our experiment, and then the probability of having our event. And the event is having a ball with diameter larger than 21.2. If you're ready, we can continue to the next topic. Do you feel like having a quick break of 4 or 5 minutes just to stretch your legs? Or you can continue with the next topic. It's a new chapter. Let me know just in the chat, quick break or no quick break. We can continue, okay. I hope the others are on the same topic, on the same opinion. Let me see. Can continue to make it an hour. Okay. So here we're going, okay, one more. So another 15 minutes. Yeah, more or less, yes, okay. So we're giving joint probabilities. And here we're gonna denote how does the normal distribution look like. So I would like you to imagine having a normal distribution like here in the graph. We have a symmetrical, we have the mean, everything is pretty straightforward. We have the normal distribution denoted by the mean, which is here in our case is 75 here. Then the variance, and the variance in our case is 20. If the variance is is that number, it means that the standard deviation, just to recall, would be the square root of the variance. And what is the difference between the normal distribution and standard normal distribution? It means the standard normal distribution is having the same type of graph, but this time we're having it between 0 and 1. There is no number that is larger than 1 or smaller than 0. Everything is between that period. And here, it's pretty easy to visualize this part. If we have z being more than a, what does it mean? If we have here and here two numbers that are symmetrical to the mean, and we have here a, and we have here minus a because they're the same numbers but with different sign, it means that that area here that is above a, that is in the blue, is exactly the same as the area that is below minus a. Because we know that everything is symmetrical, so whatever is on the right side, whatever is on the left side is just identical. And the area here that is between minus a and a, let me take another color, the whole part here, is 2 times the whole area minus 1. And why? And do you want to show you how it's proven to prove that statement? Or do you think it's fine by going straight forward and using it? I can show you how it goes. Firstly, to calculate this part here, we need to have the probability of having the area that is below A. And from that area, we have to subtract this small thing here, which is the area that is below minus A. And here, we have to compute, because in the table, we are given that part, but we are not given that part. So we have to be careful and take, having to know that those parts are identical. We just can subtract the whole probability that is below the function. Minus 2 times the probability, oops, not the probability, but z, the area that is below minus 1. So it's important to remember that in the table, the numbers that are given are just to a certain point. Something that is below A, something that is below minus A. We are not given that part here, or for example, that part. So let's continue and see that table, how does it look like, and how can we use it. So firstly, if we have to find, do you know how to find if z is more than 1.25? When we need to look at the slides, it's written on the slide, but still to. Do you know how to find those numbers here that are below the graph? The area below. Okay, I just give you the quick method to do it. It's not the method, but just the way how to do it. First thing, if we have the number that is inside the brackets, we have to take a look firstly on the first column, that is z. And we're searching for the first part of our number, which is 1.2. Here is 1.2. Then we have 5. But the 5, we have to search it here. That is the decimals part, which is that column here. So we need to find the number that corresponds to that column and to that row. So we just take a quick line here and then a quick line here. And it becomes obvious that that's the area that corresponds to this part here. If we know that here we have 1.5. If this number is 1.5, it means that the area is equal to 0.89. Yeah, 89 is just 89. And that area is always between 0 and 1. And just for a quick exercise, can you find all those numbers here, for example? What's the probability of having z being more than 0.71? You can just have a look at the table. There's nothing to calculate or write. Just see which column and which row we have to look at. Do you see the number, our number, in the table somewhere? We just divide the number in two parts. We take 0.7 firstly, and we are searching here for 0.7, which is here. Then the second part is just 1.01, which is here. And we're searching for the number that corresponds to that column and that row, which is this one. The probability of having z being more than 0.71 is just 0.7611. But what would be if we have inside the brackets but with minus? Our table doesn't show us those results, but we know that if we have a certain number as this one but with minus, those two parts here and here are completely identical. So we can just take 1, which is the whole graph, minus this number that we already know it's in the table. If we take 1 minus that part, we're gonna end up with this small here, this small one here. But this one is exactly as this one. So it's basically, they're equal. So what would be the answer if we have to look for the probability of having z being more than 1.09? I will try to. Do you want me to erase those? Are they confusing, or it's fine to orientate yourself? Okay, I will leave them. if I have to draw the graph, we're searching for Z being more than 0.71. So it means that if we have our number here, 0. Oh no, it's minus. I got it confused. So we have Z being more than minus 1.09. You have to make the calculation for that part. What can we do? We just have to search for the same number but without the minus in our table. And if we find that number, we will be given what is that part here. We can find the yellow part in the graph, in the table, I'm sorry. The yellow part, we can find it in the graph. And if we find the yellow part, we can calculate 1 minus the yellow part would be the green part. So in the table, we're searching for 1.09, which is 10, which is here. And then 09, which is here. And in the right number should be this one, if I'm not wrong. 0.8621. And if we're searching for the area that is above minus 1.09, it's the whole thing here. But the whole thing here, it's exactly the same as the yellow part. So it's basically 1 minus 0.8621. Please give me a response. Is it confusing? Is it easy? What is it? It's fine, okay. Yes, yes. So just remember that in the table, we are always given the simple numbers. We don't have minus. If we have minus, we have to calculate it on our own. So for another exercise, can you calculate the probability of having Z being more than 0.23? And type in what the number you see on the table. Exactly, yes, that's right. It's just we have to take a look at 0.2 here and 0.3, and the corresponding number is here. What would be the number if we have to calculate the probability of Z being more than minus 65? Be careful because we have minus here. Yes, exactly. Firstly, we have to have a look at 0.6, then 0.5, and the number here is 65. Yes, here. 0.7422. But that's the number that corresponds to the area that is in green here. But we're searching for the other area. So it should be 1 minus 0.7422. which is equal to 0.2578. Do you need more exercise on finding those numbers in the tables, or do you feel confident enough? Okay. I will wait for a few seconds for the others to respond, maybe in the chat or. Okay, we'll continue. And now we're having again linear transformations, but this time with normal distribution. One person just rejoined. I hope everyone can hear and see what I'm showing.
So
Okay, I will continue. We're having x as normal distribution, and between the brackets we have the mean, which is the average, comma the variance, and just a linear equation. And we have to calculate what would be the new expectation of the new variable that we have y. So could you tell me what is the distribution of y if we're given model x here? And what are the parameters that are related to our distribution? I will go straight to the point and explain how it works. We have the expectation. We have to find the expectation because in our new distribution, it consists of the mean, which is the expectation, and the variance. So we have to find them both. First, the expectation. What we do, we just take the first number that is related to x, that is attached to x in front of our expectation of x, and the rest we just copy and paste, -1. We know the expectation because here we have it's 9. So it becomes 0.2 times 9 minus 1, which is 0.8, I'm sorry. Was the expectation clear? Did you get it how it goes? Okay. Then we have the variance. It is the same, but we are only interested in the number that is attached to x, only in 0.2. So we have to take this number to the power of 2 and multiply by the variance. But the variance, we already have it because here, the second number here is the variance. So we take 2.2 to the power of 2, which is 2.24, times the variance from x, which is given, and in the end, we could result in 0.09. So we already found the expectation and the variance, so we can come up with the distribution. In the brackets, firstly goes the expectation, comma, then the variance. So that's our new distribution. And it's the same type as the given one. It's normal distribution. If you remember in the first, maybe the second slide from today, we did a tricky exercise where we are going for x, expectation, and standard deviation, and it was called standardization, that part. It is pretty often seen to use it because we have a given distribution, but we have to find the probability of having another y, because here we have y and we have to find y being more than 0.7. And using that formula, you can adapt it to our exercise. Do you want to have a 30 seconds maybe to think about the formula and plug in the numbers that are given in the formula and see if you get an answer? I will start by explaining it. We're just having a look at here. What do we have? We have y. We're just plugging y minus the mean. Do we have the mean here? It is given here. So it's 0.8. Then we had divided by the standard deviation. Do we have the standard deviation? We don't, but we have the variance. So the standard deviation would be just the square root of the variance, which is 0.09, which is equal to 0.3. We just copy and paste the standard deviation here. Then we follow what is given. We have being more, and here we have a number. So that's easy. We just have 0.7 minus 0.8 divided by 0.3. And the main point of doing that, because we have to find the number here and then find it in the table in order to get the probability of having y more than 0.7. So if you calculate it correctly, here we have to have z, because this whole thing is z. But in the table, we can search only for z. We cannot search for y. So we have to make the transformation from y to z. That's standardization. We have z being more, but we have just a number here. And if I'm not wrong, the number should be minus 0.33. And now in the table, we have to search for 0.33 and take 1 minus what we have. Can you find in the table the corresponding area to minus 0.33? Do you want me to show you again? The image with them, yes. Do you find your number here? We just search for 0.3 here on the left side of our table, and then for 0.03, which is the number 6293.
Is it 0.370?
And we have to, yes, exactly, 3707. Now we're going back to the presentation. So here we have to find the probability of having the area above minus 0.33. So if we imagine how does the graph looks like? It's that way. Then we have it that way. Here is minus 0.33, and we have to find that area. Which is the one that we found in the table. And why we don't have a -1? Why we don't have 1 minus the area that we find in the table? Because here it is, we are searching for something, the area that is bigger than our number. But our number here is with minus. And we found the table that this part here is 0.6293. But it's somehow it seems weird to have the smaller part being more, because here for that part we have 0.62, and for that part we will have 0.30, what was said in the chat, 37. But it's weird because the bigger part corresponds to a smaller number. So better when calculating those areas, draft the graph and see how the numbers below in the areas corresponds to which number. So in our case, the answer should be the bigger number because we're searching for the bigger area that is above this one here, which is 0.6293. That could be explained also by the fact that if we have the same distribution function, we're searching for the area that is here, right? But that area could also be found if we take 0.33 here. That blue area is the same as this yellow area. That yellow area is the same as that yellow area. So we have to find that area, but that area is already given in the table. In the table, we are given only numbers with plus, not with minus. So that's why we have 0.6293 as an end answer. Do you need a minute to take notes and understand what it goes behind the numbers? Is it clear, Muriel? I'm sorry if I'm pronouncing it right. Correct. Wrong. Sorry. That area is here. If you have a question, please tell me. Yes, because here we have only plus, we don't have the minus number. In the table, we are given the numbers that are only with plus. So from that minus, we transform it, because here, what it says, here it's minus 0.33. And here it says the area that is above 0.33. But here, that area is the same as that area here, right? Those two are the same. They're equal because 0.33 is identical to 0.33, is on the same distance from the mean. It's just standard. Do you have a question?
I'm just trying to figure out why this time it wasn't 1 minus z, and the other times it was.
I'm not sure I can hear you.
I was just trying to figure out why this time it was not 1 minus the number on the table.
Okay, a quick example. If you're this type of area is when it's more than the minus number, which is here. But if the question was asked the area that is below minus 0.33, that should be 1 minus the yellow area. The yellow area is in the table. So we have to take 1 minus 0.62. But we're interested in the bigger area, not in the smallest one. So whenever we have such numbers to calculate and using the table, my advice is just make the graph and compare what you have in the equation to the graph. Because sometimes I also do mistakes, but when you see that the bigger part is the smallest number, it doesn't make sense. So it has to be the vice versa. Okay, so let's go to the second question, not the second, the third one. What we know that, what can we know if the probability of having y between 0.6 and 1? Now I'm going to draw the graph again. 0.6, let's say somewhere here. And 1 is here. And we have to make the calculation for that area here. If you use the same formula as before, just this one, the standardization, you can just adapt your numbers again for that formula. But here, the only difference is that we're going to have two numbers between, y would be between two numbers. The first part, we just have 0.6 minus the mean, which is 0.8, because we are having it from the exercise, divided by the standard deviation. It would be the same with the second number we are given. So it should be just 1 minus the mean divided by the standard deviation. And that is z that we are interested in. So here, if we compute it, we're going to have minus 0.67, then y being less than 0.67. So what it means that here, the z being less than 67 should be, sorry. So it means having the graph, having here 0.67, that area is on the left side, which is here. We can find it directly from the table. If you find 65, you will have this number here. So now I will go to, we're searching for 0.62, 0.62, oops, I have to, 62, so we're here. No, I'm not 67. Sorry, 67. We're searching for 67. So we're again searching for the 6 until the 7th one. The 7th one is here. So our number is 7486. So just remember 7486. Go back to our slide. And we have the first part. So now we have to do the second part. We have the area that is below 0.67. And that small area is basically 1 minus the area that we just found. Was that clear? And it's just a matter of calculations to get this number here. That would be 0.22. And 0.74 minus 0.25, it would be equal to 0.49. Do you have a question? If you remember, we had an easier way to calculate it. I'm not sure if it's easier for you, but you can just take the number that we got from the table, that is the green area here, multiply by 2, and minus 1. And why because minus 1? Because when we multiply that area, we're gonna have the whole area below the graph double, counted twice. It's doubled. So we have to take the minus. In that way, we're gonna end up with the number here. It's the same number. Please let me know if you have a question or any doubt, or if I did a miscalculation or anything. Was it clear? Just type in yes, no, it's, yeah, okay. No question is clear, okay. If that's the case, we can continue. I'm not sure. We are way over 1 hour. Do you need maybe 5 minutes for a quick coffee and something to drink? Or you're fine to continue? A break would be nice. Okay. So we are having a 5-minute break and we are back at 11:45. I'm here if you have a question or anything.